I don't know what we did there.
Patrick and Stephen, are you on and can you see my screen?
Yeah, looks good.
Okay.
All right, so hello everyone, we're Team 6, also known as MARTI, which stands for Mesocyclone Aircraft Research Technology Initiative. So for the agenda for today's meeting, I'm going to briefly recap our team structure and our mission statement. Then we're going to go over some issues that were raised from MCR. Then we're going to cover our design requirements and our preliminary design solution. And then we'll conclude with a risk assessment, cost, and our timeline. So for our team structure, our coach is Ping Wei from Iowa State, along with his TA Anwar. For project lead, we have Brenton from ISU, Chief Engineer Stephen Lim from Purdue, and our team consists of students from Iowa State, Purdue, and University of Washington. And the rest of our team is broken down into those 5 sub-teams. So for our mission statement, current ground-based weather data acquisition systems are only able to predict tornado formation a few minutes before they occur. But if meteorologists have data from within the storm at different altitudes, they can actually increase these prediction times up to an hour before tornado formation. So our team is defining building the Marty McFly aircraft, which is an extreme weather data acquisition UAS that will be deployed by storm chasers into storms to collect temperature, wind speed, humidity, and pressure data. So our UAS will fly to an area of interest called the rear flank downdraft, and it will collect weather data using these 3 deployable sensors called drop zones. So some of the issues that were raised from MCR include there's a lack of correlation between our design requirements and the stakeholder. So to remedy this, our team met with a few more stakeholders. We actually got connected with a scientist from the National Center for Atmospheric Research, and this will all be covered in slides 6 to 10. Another issue was that it was hard for us to test our aircraft in a representative environment to make sure that it would withstand all of the weather conditions. So we looked into impact testing of composite materials, as well as flight testing in inclement weather, and this will all be explained in further detail on slide 28. And the last issue was that it would be hard for us to waterproof the aircraft, so what we did was we researched similar UAS applications to see how they did their waterproofing, and this will be covered in slide 30. So for our mission stakeholder, we have Dr. Robin Tanamachi. She's an assistant professor here at Purdue. She has research interest in severe convective storms and tornadoes, and she helped us, she provided us a location of interest in these storms, as well as general weather conditions that our aircraft will be expecting. She told us that worst case, we'll be seeing 30 meter per second gusts in all directions, as well as light precipitation. And she also referred us to the Vortex 2 project that she was involved in. And this project was back in 2010. It was the largest tornado research project in history. And part of this project was actually some scientists looked into using UAVs for weather data collection. So we looked at their operations plan and used that to help form our mission profile, which you can see here. So on the left side, we have our flight path diagram. This is an image of a storm. And on the bottom, our aircraft is taken off from the ground station, flying 1.5 miles to the rear flank downdraft, deploying 2 drop zones at 2,500 feet, and then flying this zigzag motion to collect data from both sides of this air mass boundary, and then deploying the last drop zone, and then returning back to the ground station. And on the right is the altitude diagram. Our aircraft will fly 1.5 miles, climb to 2,500 feet, deploy 2 sensors, cross the air mass boundary multiple times, deploy the last sensor, descend, and return back to the ground station. So with this, we have our updated design requirements. Our aircraft will fly an 8-mile range, cruise at 67 miles per hour, be able to reach speeds of up to 88 miles per hour, fly at 2,500 feet, carry and deploy 3 drop zones, which you can see on the right are the yellow cylinders. It will be able to tolerate 67 mile per hour gusts, withstand potential small hail impacts and be water resistant, and it will be hand launchable. So for our payload stakeholder, we have NCAR scientist Holger. He specializes in sensing and instrument development, and he provided a lot of insight regarding the drop pod deployment, how they deploy their parachutes, as well as the data transmission. So he told us that for our application, it would make sense to use a handheld radio receiver to receive the data real time from the drop pod. And NCAR was actually nice enough to lend us a few drops on and the radio receiver all for free. And one of our team members is going to go pick that up soon. So for our payload definition, our aircraft will be carrying 3 NCAR mini drop-ons. This will allow for a triangulation of weather data. These drop-ons have built-in sensors that measure pressure, temperature, and humidity, as well as have a built-in accelerometer, GPS, and radio transmitter. And for the dimensions, there are cylinders that are about 1 3/4 inch diameter, 12 inches long, and they each weigh about 0.367 pounds. And they descend at a rate of about 30 feet per second, which is about an 80-second drop when deployed at 2,500 feet. So for our payload location, we had a short trade study to see how we would mount the payload to our aircraft. We looked into mounting it inside of the fuselage, so this led to a much more complex release system, and having a door in the fuselage that opened would hurt our waterproofing efforts, and it would require more surrounding structure. But the only benefit that we saw was that it would potentially reduce drag. But we ended up just going with an exterior mounted payload for simplicity, which you can see on the right.
Okay, so I'm going to take it over from here. I'm Stephen from Purdue University. First thing for aerodynamics that we did was select out an airfoil that would be suitable to our mission. On the left, you can see a table of different airfoils we considered. And although we had great results from one of the MH airfoils, as you can see, we didn't want to really go with it because it had quite a large cut towards the trailing edge of the airfoil, and we wanted something that would be very sturdy for our application because structures, as you will see, is a major issue going on. And so we picked out the RG14 airfoil because it has very good drag values at high speeds. That lower drag value would also help us to have a less powerful propulsion system, which would be very costly for our application here. So for the wing design, we wanted obviously a strong structure. We wanted low drag. We did a taper trade study, and we found that about 0.5 is suitable for application. Also provides a good efficiency. We also wanted to be on the higher side for aspect ratio to lower our induced drag values. And we decided to opt out of dihedral for simplicity and more structure. And on the right here, you can see we considered where we would place our taper. Do you want to have it symmetrical on the back side or on the front? And we went with the option on the left side of this right image because because of the chance of hails hitting our aircraft, we don't want our leading edge to be damaged. And by putting an angle to that, we can have a small deflection of the hail. So that increases our chances of survival. So once we put together our airfoil, we went ahead and designed the wing for our aircraft. We have an aspect ratio of 8.8, a wingspan of 1.8 meters, taper ratio of 0.5. Our root chord is 0.272, tip chord is half of that, 0.136, and our area is 0.366 meters squared. And our wing loading is 9.3 kilograms per meter squared, or about 91 newtons per meter squared. Next thing we did was go on to the tail design to balance out our wing. We went through the standard volume calculations, and we got a horizontal tail with an area of 49 inches squared, span 14 inches, root chord 6 inches, aspect ratio of 4, taper of 0.5, vertical tail, area of 38 inches squared, height 8.7 inches, root chord 5.8 inches, aspect ratio of 2, and a taper ratio of 0.5. We went for the NACA 0010 right now because it just proved to be a very nice fit. If our wing or anything changes, we may consider moving up to a 12, but currently NACA 0010 is perfect for us. And so we went ahead and analyzed all this in XFlyer, and the calculated lift we need at cruise requires a CL of about 0.165. And once we balance out the tail at about a meter away from the wing, we found that our CM0 is at around alpha 0.5. And at that exact same alpha, we have a CL of 0.168. So this balances out really nicely for us. Next slide, please. And our CLTE at that cruise speed is about 17. And then when we pitch up to climb, we get slightly higher CLCD. So that's nice. Our CD is also on the right, which is really quite low for this wing and plane in general because of our choices of airfoils. So here's the overview of what the plane looks like in Xfire for our analysis. And moving on to propulsion system, we consider a twin prop and a single prop design because we want to compare the differences. So for our propulsion system, if we went with a twin prop, this would be our setup ESC of 2 times YEP 80 amp continuous current for each motor, which is a Sunny Sky 2820 920 kV motor, and 2 propellers of ABC 10 times 10E, and a battery, 2 batteries of Zippy Flight Max 2700 milliamps. However, we wanted some more simplicity in our design right now, so we went ahead and opted for the single prop since it had a slightly higher efficiency also. This would require an ESC from Castle Creations of 100 amps continuous current, a motor from Scorpion's S2 330 kV motor, a propeller from ABC E13.5 by 13.5, and a 2 times battery from Zippy Flight Max of 2,700 milliamps each. 4 cells in series, so we have 8 cells effectively. So the pros of single props here, we have slightly higher efficiency, we have less complexity, hence we have a lot more structure that we have to worry about. The twin prop really doesn't offer too much benefit and redundancy. But the twin props are a little less expensive because the parts aren't so extreme. There's more power available outside of cruise, and the aircraft still has some power available if one system fails. For the avionics, we plan to have a Pixhawk 2 autopilot. We'll control this mostly through Mission Planner. And for our receiver, we have a Spectrum AR93509 channel because 6 channels for the aircraft, 3 channels possibly, leaving that room open for the drop-ons. Our ground control station will have dynamic trajectory planning to track the moving storm. We'll use real-time radar data from the weather teams there, and we'll have to determine the waypoints for the flight in real time. And as Patrick said, we'll have a handheld receiver radio for the data from drop-ons, give us all the weather data we need. We'll have a computer on the ground station to control the UAS, and this will be, as I said, through Mission Planner and a receiver antenna out to that ground station, and a database for telemetry data and drop-ons data. So overall, here's our performance summary. We'll have a plane weight on our sizing sheet came out to be about 7.5 pounds, range of 8 miles, endurance is about 13 minutes. Flight ceiling, we're aiming for 2,500 feet if we are able to get such permission. Cruise speed of 67 miles per hour, dash speed 88 miles per hour. Takeoff thrust is 8.4 pounds. Cruise thrust is 2.4 pounds, and our glide distance is 67,500 feet. So for our weight and balance, we wanted a slightly higher sag margin because of the strong gusts that are occurring vertically during this tornado. So we went for 30%, and you can see our chart on the right listing our weights. And so payload is located at the CG, so when we drop those, we won't really have a problem of our airplane CG shifting and our stability going crazy. And CG is located at 13.4 inches, so that's where we'll put our payload. So we just went ahead and did the calculations. So our desired static margin is obviously 30%, so we calculated for that. And found our aerodynamic center to be 13.1. We placed our center of gravity at 13.4 inches to achieve the static margin, and our neutral point is back at 14.5 inches, and that data is from last slide.
This is Brenton at Iowa State. For our VN diagram, our normal maneuver envelope was developed with a maximum load factor of 4 Gs and a minimum load factor of -2 Gs. And that is shown on the left in blue. Once we incorporated in the possible gust loads, a new envelope was created with a maximum load factor of 8 Gs with a minimum load factor of -6 Gs. On the right, outlined in red, is the gust envelope that we have found. So for aircraft testing, due to our unique mission, a real-world test of our capabilities will probably not be possible. To overcome this challenge and validate our design in storm conditions, we can perform a finite element analysis or some computational fluid dynamics in computer models. A scale model can also be used in the wind tunnel to test our design at the high speeds that we are anticipating. Another possibility is testing our autopilot stability system in less than favorable conditions, such as high wind, not quite a storm, just a high wind day, to see how our control system works with the wind. For the hail impact testing, as was brought up in our MCR, per our meteorological experts, the worst case scenario for hail that we may encounter is golf ball size. We idealize that as a sphere and estimate that to be about 20 meters per second impact. We could physically test material coupons that we have in different materials to see if they could survive such an impact, and that way validate that our design will be sound for such a mission. So for waterproofing, in order to achieve our waterproof design requirement, we designed a mostly sealed fuselage, as was seen with the exterior drop-ons. A small screen vent can be used to keep out water while allowing an air exchange to mitigate the electrical components heating. A sealant such as epoxy or other waterproofing spray can be used to shield the electronics from any possible moisture. So for risk assessment, this is a risk assessment matrix which describes the rating of mitigation required for each hazard. A 9 or high mitigation will mean the mitigation needs to be followed every time and needs to be specific to keep from causing a catastrophe. A 2 or minimal mitigation means that it should be something we check every couple of flights and should not pose a threat to our mission or people. Risk severity is how dangerous the hazard would be if it occurred. The danger is measured by a level of injury on a person or the mission systems. Risk probability is how likely the event will occur. We ask people with experience to say, how many times they witnessed such a hazard occurring. So all that culminates down into a shortened list that we provided. We have the full list in the appendix. This shortened list of hazard scenarios that we came up with, a lot of mitigation for our hazards to have us inspect the aircraft before and after the flight, meaning we'll need to create a flight checkoff list. As you can see, these the risk assessment values link back to the previous slides and just discussing how we came up with these values and how we would go about mitigating these risks. Our cost, the cost breakdown, the total budget is shown in the pie chart. These exact values are shown in the table on the left. These values are inflated to account for replacement or backup parts, such as extra propellers, ESCs, other sort of things. These values are, our total cost is estimated at $4,264, leaving a good remainder size for any other unseen circumstances. We have also factored in the glider expense as well. This side shows our Gantt chart to plan and track our progress as we work towards our preliminary design review. We were very ambitious when we set our goals for the detailed design of our craft. Although we did not complete as much of the detailed design as we had anticipated in Phase B, we're still on track and ahead of schedule to enter into Phase C to nail down more of those the detailed structures, the FEA, and into the CFD. So for our next phase, Phase C Gantt chart, the slide shows Phase C and our proposed schedule for finalizing design and systems and begin to fabricate our glider. So that concludes our presentation. Thank you for listening, and we will now open it up for any questions.
Good morning, guys. It's Alden Black from Boeing. Great job. Love the mission that you guys picked. You have some pretty interesting and challenging requirements, so I commend you there. And I also like the emphasis you put on really trying to keep your aircraft strong, because you'll be in a very challenging operating environment. If you could flip back to slide 27, please, for a second. That's your VN diagram. So you obviously have some very high load factors here that are going to drive a lot of weight into your aircraft, right? What are some of the perhaps design choices or trades you could do around your wing in particular that might lessen the severity of your VN diagram there to make your structure overall a bit lighter and easier to make.
Yeah, it's Philip here, also at Boeing.
So anyway, so I put that question out there first. I have an answer in mind, but I don't just want to tell you that answer. I want to see if you can get there yourself. So I'll ask again, what are the design trades that you could do around your airfoil and your wing planform that would help mitigate the impact of gusts on your VN diagram?
Sorry about that. We thought we heard another question coming in. That's why we
Not
on the
very
response. Stephen, I believe you working on the structure. We talked about spars with experienced RC pilots that have come to a couple of our meetings, and we talked about just changing the overall, lessening the aspect ratio to reduce that moment on the route. Stephen, do you have any more on that?
Purdue here. One thought that we have is we can shorten our wingspan to lessen the moment of run that will be caused from the gusts. This will make for a much more stable aircraft, and with a shorter wingspan, our structure doesn't have to be as complex to support the wing all the way up to the tip.
We'd also be reducing our surface area for the wing to act on.
Right. So certainly the latter, reducing your wing, making your wing loading higher, so a proportionately smaller wing will make it less susceptible to gusts. If you think about like a commercial aircraft at a really high wing loading compared to like a general aviation aircraft, which is a much lower wing loading, the general aviation aircraft is going to get kicked around in turbulence and gusts a lot more than a big aircraft because there is proportionately less weight per square area of wings. So that's one thing. Reducing or changing your aspect ratio to reduce the bending moment at the wing root. Yep, that's certainly an impact. Don't forget too that a lower aspect ratio wing effectively flattens your CL versus alpha curve, so that changes in angle of attack from gusts have less of an impact on your lift coefficient. So again, just to use an analogy of like a fighter jet with a delta wing, a very low aspect ratio wing is less susceptible to gusts than a glider type aircraft because they can achieve a higher angle of attack. The third thing too, and you did this, I'm not sure if it was intentional or not, but a less cambered airfoil in the same vein has a less steep CL versus alpha curve. So again, it's going to be less sensitive to gusts. So I would encourage you to keep using that airfoil that you've picked. But overall, I would encourage you guys to go back and try to do a trade around your wing loading and your aspect ratio to see how high you can push your wing loading and how low you can push your aspect ratio to still meet your cruise numbers, but see how much you can push it in those directions to lessen the severity of gusts on your VN diagram, because that's going to drive, because of your mission that you picked, a lot of weight into your structure if you're not careful.
Hi, it's Philippe, also at Boeing. I would use a thicker airfoil than 9% to get more strength for the same structural weight. I'm also a little concerned about not having dihedral. If your airplane doesn't have very good spiral stability, I don't know that the autopilot can deal with that. And my third question is, if you increase the wing loading, can you still hand launch the airplane? I missed the beginning. Is this a hand launched plane?
Yes, yeah. One of the few design requirements that was set forth in this project is it has to be hand launched.
So do you have an estimate of launch velocity? Are you confident with at that weight? And especially if you start increasing the wing loading, that you can still do that?
Currently, our wing loading is pretty high up there already as part of the design process, but currently need flaps to take off. Our thrust to weight ratio is 1-to-1 about approximately right now, and with our CL max for the airfoil, we're on XY is only computing about 1.0 CL max, and we need like on the sizing sheet, if I put in like 1.2, it'll take off, but at 1.0 it won't. So we're gonna have to the next step I was going to do was to analyze flaps for the aircraft to make it launchable.
And a thicker airfoil would also give you more CL max. It looks more like at least 12% than 9%.
Yeah, it's a consideration. We were thinking we wanted a bigger airfoil for better structure, but we also wanted to see our drag value at a lower thickness. So it's a trade-off. We'll look into it.
Okay.
Hi, Branko Lukic here. I would just like to add the comments about the wing dihedral. Definitely, I've written those down. I think this airplane, the primary mission is to fly in a pretty turbulent conditions, really challenging. I think what you need to do is increase stability of that airplane with anything that you can, and one way to do it is to add the dihedral. But you also want to consider a high wing rather than a middle wing airplane configuration. That is also enhancing stability of the airplane. If you look at the typical star chasers like C-130, retrofitted to fly into the Hurricane, those are high wing airplanes and they're way more stable. Also, as I said, there will be a lot of turbulence, some high wing up. The single boom tail shown in your design as a constant cross section may not provide. I mean, I don't have numbers to show or prove or disprove what I'm saying, but just by experience, a single constant cross section tail boom may not provide sufficient stiffness for the tail command surfaces. You may want to consider something more than just a straight cylinder. Maybe variable, or maybe go to more robust dual tail boom design. Definitely gonna enhance endurance of your airplane in a challenging condition.
Yeah, thank you, Branko. Our RC expert that has sat in on a couple of our meetings raised similar questions. So we've been talking over the trade-off between the boom and just a full fuselage all the way to the tail.
Are there any more questions for the team? We've got a couple more minutes. Well, if there are not, we appreciate the comments. Certainly, these are great comments for the team to consider moving forward and how to address them. Again, I would remind you, if you just came on, please use that Qualtrics survey that Kathleen distributed to you for feedback. Get questions, comments, or concerns, and you didn't get a chance to get in and ask them, please write those down and send them to either me or Kathleen so we can distribute them to the team. But with that, we will move on to the next team. That team is team number 3. And I would remind you, if you just mute your microphone if you're not talking, and then unmute when you have a question or speak. That would be great. So.
Hey, excuse me, Dr. Mako.
Yes.
How do you share screen again?
You should be able to go up to the top of your WebEx. Let's see here, and go up to share, and then my screen. Are you able to see that, Julian?
Where did you go?
Just go to whatever the drop-down menu is, and say share.
I'm in.
Were you able to find it, Julian?
It's not showing up. I don't have a drop-down screen.
You have you're on a PC?
I'm on Mac. I have the buttons at the bottom. I got the eye in the top left-hand corner.
Probably your full screen, I would imagine. So if you go up and sort of highlight over where the menu buttons would be, so you'll see something that says WebEx, File, Edit, Share, View, Audio, Participant, Meeting, Window, and Help.
Yes, sir.
Yeah, so next to Edit, there should be something that says Share. Do you see that?
Or Tyler, can you do it? If he can't share it. Should be in there.
You are the presenter. I just need.
No, sir. I'm trying to see what's.
Were you able to find it?
We are still trying to figure out, Dr. Marco.
Okay, Dr. Khan. I think Shift Command K allows you to share.
Shift Command K.
Yeah, so Shift Command and then K simultaneously.
Is it Mac?
Yes, sir.
Yeah, he has a Mac, so that's why I think.
Okay, so maybe Control Command K.
Tyler might be able to do it.
I think you still are the host, so probably doesn't have the host.
I made him the host.
Oh, you did?
Yeah.
Yeah, it's asking for a host.
Okay, but I passed you the ball. Okay, do we have a backup on the sharing? Tyler?
Go
Okay.
ahead and share.
Yeah, I'm working on it.
Okay.
Thank you, Alex.
Yeah, right next to this, there's gonna be like 4 rings there. 3 rings, they're great, yeah. 3 rings upstairs for people like watching. Tim has them.
Tim has it?
Yeah. What's that?
Peer review?
I do, they're right here. I think I'm making progress.
Hey, Mike, you need to get on mute.
I'm sharing.
Okay, so somebody share. We see a screen. Again, a gentle reminder.
Did you get the cover thing printed out and stuff?
Boom, solve that problem. I have the power to mute people. So I think,
Oops, Tyler.